Welcome to Aero 210 review for GR1. This is going to be a high-speed pass over all the topics we've discussed in the last 13 lessons. It is not a replacement for the lessons, but merely designed to remind you of all the topics we've covered so far. You should also not consider this a substitute for studying. But if you can sit down and explain these concepts to your roommate, you're going to be in good shape for the GR. So this is the roadmap of Aero 210. So far, we've looked at the atmosphere, we've done a lot of fluid mechanics, and we've looked at the how do we calculate the lift and drag of both 2D airfoils and wings. So we'll go over all that. We're all building up to how an aircraft flies. So we've done a lot of aerodynamics and fluid mechanics. And the second half of the course, we're going to get to the flight mechanics as well as stability and control, all building to that aircraft design and the AETF redesign of the F-22. So the desired learning objectives are always a good place for you to you step through these and ask yourself, do I know that? Do I know that? Can I answer that? Each of these are great for reviewing everything. Flow properties, hydrostatics, we're going to go through each of these. Again, just a very, very high-speed pass. All the way up through airfoils. The airfoil lab, material in the airfoil lab is certainly testable. And then finishing with 3D wings and high-lift devices. We've not done whole lift and drag, and we will not test you for that on the GR. So in your course materials, there is a PDF of fundamental equations to know. The top half of that sheet is what's depicted here. These are all things that you should have memorized. You should not have to look these up. Of course, it's open book, so there's nothing keeping you from looking it up. But if you have to look up the definition of dynamic pressure, Q equals 1/2 rho v squared, or mass flow, m dot equals rho AV, you are not going to have enough time to finish the review. The definition of Mach number, if you have to look that up, you're not going to have enough time to finish the GR. So these are all things that should just be ready at hand to answer. All right, we started the course. One of the very first things we did was the sizing equation. And of course, we applied it to, we looked at the Stratolauncher as an application and saw how accurately we could predict the actual size of the Stratolauncher. We also looked at F-22 compared to NGAD with the sizing equation. So certainly fair game. We also introduced the concept of G-facies. And we are not going to require G-facies on the exam. The format for the exam, there's about a dozen multiple choice questions. Some of those require you to actually solve, do some equations, calculate some things, and then check the most correct answer. And then there's 3 longer workout questions, multi-part. You do not need to use G-facies. However, it is still a good mental thing for you to go through. What am I given? What do I need to find? What are my assumptions? Do I need to draw a picture in order to solve the picture, in order to solve the question correctly? Very significantly, and let me emphasize it one more time, sanity check. This is actually, in my opinion, more important than the correct answer. So if you get down to the bottom and you get an answer that just does not make sense on the GR, you're going to lose points for not having the right answer. But if you write, this doesn't make sense, I know this is not correct, the lift to drag ratio should not be 200, it should be closer to 20, as an example. That is a reflection of good engineering judgment. If you can then say, I think I went wrong here, this part does not look accurate, you are going to lose points for not getting the correct answer, but you're going to get points for exercising good engineering judgment, which at the end of the day is more important than having the right answer, because then you know to go and get and find the right answer. All right, so we spent several lessons talking about fluid mechanics. And by fluid, we mean anything that takes the shape of the vessel. So liquids and gases are both fluids. In a solid, all the molecules are locked into place. In a liquid, and actually in a fluid, they're free to move around. The distinction, what distinguishes a liquid from a gas, is primarily the density. In a liquid fluid, the molecules are close enough together that intermolecular forces can dominate the interactions between the molecules. In a gas, if we take a look at water vapor versus liquid water, the density is about 1,000 difference. So every molecule is in 3 dimensions is 10 times as far as it is in the liquid state. Because those molecules are so much further apart, those intermolecular forces are not as big of a factor as the kinetics of the molecules running into each other. The perfect gas law we use, so P equals rho RT. The R in this equation is not the R that you used in high school chemistry if you use PV equals nRT. That was the universal gas constant. But since we are always dealing with air, then we're going to use the R value for air, which is 1716 foot-pounds per slug Rankine, or 287 joules per kilogram Kelvin. Again, one of those pages that if you don't have these memorized, then I would definitely have that constant page tabbed in your book. Another thing that we talked about is the speed of sound. The fact that the gas molecules are all moving around and that pressure disturbances and density disturbances, fluctuations are going to be transmitted through the fluid by the course of the molecules running into each other. The faster the molecules are moving, the faster that information will be transmitted. The average kinetic energy of the molecules, so here we go, the average kinetic energy of the molecules is actually the temperature. Boltzmann's constant here is just a conversion factor from kinetic energy into units that we refer to as temperature. One thing I didn't highlight that's probably definitely worth foot stomping, you need to have, anytime you use the ideal gas law, absolute temperature. So in all intents and purposes, in this course, anytime you deal with the temperature, deal with in absolute temperature. So convert from into Kelvin or Rankine, so add 273 or 460 to the centigrade or the Fahrenheit. So the faster that the molecules are moving, speed of sound of the molecules is the square root of gamma RT. Do not worry about the derivation right here. We'll cover this in Aero 241 for the aerometers that go on to a compressible fluid flow. And then the Mach number is just the ratio of the true air speed that you're traveling relative to the speed of sound of those molecules. All right, so page 115, one of those pages I would definitely tab in your textbook. If I haven't mentioned you, there is an equation sheet as well as open book for the GR. We're going to start over here with the hydrostatic equation, and then we'll move to as the fluid element. So we're going to start with a fluid element that is just sitting in space. So hydrostatic, static meaning no dynamics, it's not moving, hydro meaning fluid. And so we're going to stack these fluid elements up on top of each other. And because they're stacked up on top of each other, the weight of the fluid elements on top are squishing the ones on the bottom. And we're going to realize that through a change in pressure. So by applying Newton's second law in the vertical direction, we get, and then canceling the terms that cancel out, we end up with this equation right here known as the hydrostatic equation. And so as we go up in altitude, because it's negative sign, so as altitude increases, so as we get higher in that stack, the pressure is going to decrease. So the fluid elements that are getting squished the most is the one on the bottom, and the one that's getting squished the least is the one up on top of that stack of fluid elements. We can then take that hydrostatic equation, we can integrate it up. And if we do that, we end up with the manometry equation. Now notice we pull density and gravity out here, which means that if we pull those forward out of the integral, that means that they had to be a constant. In atmosphere, the density is going to change as we go up in altitude. So we cannot apply the manometry equation in the atmosphere. We're going to have to do something else when we derive the standard atmosphere. But if we're dealing with this device filled with something that's perhaps incompressible, where we can treat density as a constant, a manometer, then we'll be able to. And we saw this in the Airfoil lab, where we had a bank of manometers filled with oil. And we also saw in the Airfoil lab where we had a barometer that was calibrated actually in inches of water. So a barometer is merely a manometer with one of these sides sealed. And you end up with very, very close to a vacuum. You actually, if you take imagine taking a tube of mercury and dumping it very quickly upside down in a pan of mercury. If it's at least a yard long, the mercury is going to fall down until the hydrostatic pressure, the weight of that fluid element, is balanced by the atmospheric pressure, pushing down on this pan of mercury right here. This is going to be very, very close to a vacuum. It's actually going to be at the vapor pressure of mercury, which is very, very low. So for all intents and purposes, a vacuum. And so then we have the this form of the manometry equation, which you could refer to as the barometry equation, which actually lets you convert pressure, which has units of newtons per square meter or pounds per square feet, units of pressure, into a length dimension. So we can actually measure pressure in inches of mercury, say, which is exactly what the ATIS gives you when you go down and fly at the airfield. They'll tell you that the airfield altimeter is 3016, which means it's 30.16 inches of mercury sea level atmospheric pressure on that day. All right, so that actually introduces 2992, 29.92 inches of mercury is standard pressure at sea level, 15 degrees centigrade, 59 degrees Fahrenheit. If we say standard day in a problem, that means that you can just go to the standard atmosphere tables and look it up. So if we tell you 20,000 feet pressure altitude, you can go to the pressure column of 20,000 feet and pull the value there. If we tell you 15,000 feet temperature altitude, you can pull the temperature value from the 15,000 foot. You may not be at 20,000 feet or 15,000 feet, but the pressure and the temperature are there, which then lets you tell what the density of the air is. You can calculate the density by using the perfect gas law. Of course, convert temperature into an absolute value. So we have two equations. We have the perfect gas law and we have the hydrostatic equation, but we have three thermodynamic unknowns. We have pressure, temperature, and density. And so the way the standard atmosphere was defined, recall, is that we had this standard temperature profile through the atmosphere, through the four different layers: troposphere, stratosphere, mesosphere, and thermosphere. And those layers are actually defined by where does the lapse rate, how does the temperature change with altitude, where do those characteristics change? That defined each of the layers. Not something that you'll need to do on the GR, but this is how you actually integrate up those different layers. We'll have you program this up in 206 so that you have your own standard atmosphere model. And this is what it looks like when you do. So here's the atmosphere table from the 1976, or the temperature profile through the standard atmosphere from the 1976, all the way up past the von Karman line, which is at 100 kilometers, 328,000 feet. And so you'll do that. All right, so that is the hydrostatic and manometry. Now let's take a look at continuity, which is conservation of mass. So matter cannot be created nor destroyed, at least not in this class. And so if we have a tube, matter's coming in, and so long as it's not stored in this tube, the same amount of mass has to come out. And so if we take the derivative of that, then you can get the mass flow rate, m dot equals rho AV, one of those equations you want to have memorized. And because this is true, we can actually look at any 2 points and equate the mass flow rate there. So rho AV equals rho AV at any 2 points in the airflow, so long as we're not storing flow. If the density does not change, i.e., so for a given mass, we cannot change the volume of that mass, i.e., we can't compress it, so it's incompressible, density does not change, then we can just merely cancel the density values out, and we have the incompressible form of the continuity equation. Where does that occur? So as the airflow changes, the density is going to change. As air starts moving away, the density is going to decrease. But as a gentleman's agreement or gentlewoman's agreement, we'll say, hey, if it's within 95% of the total density of the stagnation density, then we're going to say it's incompressible between friends. And so that occurs below 0.3 Mach. So anywhere it's below 0.3 Mach, we can use the incompressible form of the continuity equation. And we just need to know the area and the velocity, and we can tell the area and velocity anywhere else. 0.3 Mach corresponds to 330 feet per second, 100 meters per second, 200 knots, or 230 miles per hour. Again, you should probably have those ready-made so that you can very quickly know whether or not on a problem you need to calculate the density in order to calculate the mass flow, or calculate the change of velocity due to a change in air, for example. If you're faster than that, then you need to use the full-up compressible form of the continuity equation. So this gives rise to the very interesting characteristics. So mass flow rate is m dot equals rho AV. We can also look at the volume flow rate, which is just area velocity, area times velocity. And so the very interesting fact that the amount of air going through the two engines on the Boeing 777 is more. There's over 100,000 cubic feet per second of air going through the two engines, the two GE90s on the 777. Then water by volume goes over Niagara Falls. Pretty fascinating fact. All right, so that's continuity equation. Now let's take a look at a fluid element that's moving along a streamline and apply Newton's second law to that. So fluid element moving along a streamline. If there's a pressure difference, so i.e. a force, greater force pushing on one side or a lower pressure, less force pushing on the other, it's going to accelerate by Newton's second law, F equals ma. The acceleration means that there's going to be a change of velocity. So you've gone through the derivation in your textbook as well as in class. Newton's second law, which is the conservation of momentum, gives rise to Euler's equation, dp equals minus rho v dv. So this means that if the velocity is increasing along a streamline, that means the pressure is decreasing. So think about the fluid elements along a streamline moving faster along the streamline. That's going to decrease the pressure on this side. And actually, that's what causes that fluid element to go faster because, hey, there's more room. It's going to be easier for me to go. We can integrate, just like we did, we integrate up the manometer equation, we can integrate up Euler's equation. If we do that, now again, that density is going to be problematic unless we assume it's incompressible, and let's just pull it out in front. So if we assume incompressible, we can pull that out in front, we can integrate it up, and we get Bernoulli's equation. And then rearranging terms, we get the fact that we have static pressure plus dynamic pressure is going to be constant anywhere along a streamline. And that's in the static pressure plus dynamic pressure is what we refer to as the static pressure or stagnation pressure. And of course, that's how we described how lift occurs. So the stream tubes, due to the fact that the same amount of mass has to go through these stream tubes on the top, and that they, by continuity, those areas, stream tube areas, are smaller, so velocity is higher. Because velocity has increased, dynamic pressure has increased. Well, total pressure is constant, so the only way dynamic pressure can go up is if static pressure drops. Therefore, you end up with this lower pressure, that's what the red is here, lower pressure here, higher pressure, that's what the dark blue is. And so that pressure difference between the bottom and the top is what gives us lift. It's also what gives us pressure drag. So if we look at the difference of pressure on the front side of the airfoil here, so we can see quite a bit of high pressure here, and some lower pressure here on the backside, that pressure difference is going to result in pressure drag, one of the two types of 2D drag that we'll talk to. And here's just a quick animation. You can see how quickly the stream tube here, it gets squished over the top. The fluid elements move much faster. Dynamic pressure goes up because the velocity is higher, which means static pressure goes down. So we get this lower pressure area on top, higher pressure area on the bottom, and that's what gives us lift and pressure drag. So something that is a frequent point of confusion and often missed on GRs. So again, total pressure is constant everywhere along a streamline. So if we look at, we've got some streamlines moving through a venturi here at 10,000 feet. So the density at 10,000 feet is right here, 1756 slugs per cubic feet. And then we got the pressure, static pressure is 1456 pounds per square feet. And if the air is moving at 100 feet per second, and it's moving through this venturi that starts at 2 square feet and drops down to 1 square feet. Again, if we look at continuity, A1 V1 equals A2 V2, we see we're still only at 200 feet per second. Therefore, we are incompressible, and we don't need to calculate density. And we can apply Bernoulli. So if we take a look at the total pressure here at, let's call this station 1. So we look at the total pressure. Static pressure is 1456. The atmospheric pressure at 10,000 feet. Dynamic pressure, so if we take 1/2 rho v squared from 100 feet per second, there's the density, so 1/2 rho v squared, 100 feet per second, 9 pounds per square feet, which adds to our 1456 to give us a total pressure at point 1 of 1465. So 1465 pounds per square feet of total pressure at station 1. It's also at that point of the streamline, also at that point of the streamline, also at that point of the streamline, also at this point of the streamline, right at the throat of the venturi. So we know here, because we're told that the throat is 1 square foot. So based on the fact that it's 1 square foot, we know that the velocity is 200 square feet, which lets us calculate what the dynamic pressure is. Again, assuming that the density is the same, because the fact that we're incompressible and the density hasn't changed. So the fact that the dynamic pressure is now 3,500 or 35 pounds per square feet, so it's increased, and the total pressure is still 1465, that means the static pressure had to drop 1430 compared to 1456. Just what we'd expect. Total pressure constant, pressure constant, 1465, 1465. We enter this pitot tube, still 1465, all the way there to the end of the pitot tube, where it has stopped. So at this point, at this stagnation point, i.e. the velocity is 0, the total pressure is going to equal the static pressure. But the total pressure still has to be 1465. So the static pressure is 1465, even though this pitot tube is at 1456 or at 10,000 feet of pressure altitude. So the ambient pressure is 1456. But in the pitot tube, the static pressure has absorbed the kinetic energy of this air molecules, these fluid elements that have stopped. This could also be, we've drawn it here as a pitot tube, but this could also be the leading edge of a wing. So there is a static pressure on the leading edge, static point on the leading edge of the wing where the velocity is 0. And what is the pressure? What is the static pressure at that stagnation point? It is the total pressure along the streamline that led up to that stagnation point. So in this case, 1465. Very, very commonly missed question on the on examinations and on finals. All right, so we just had a pitot tube right here. If we take a pitot tube, so here's a streamline coming in, pushes on, in this case, a manometer here. So we have higher pressure where the total pressure here, where the static pressure is. And then the atmospheric static pressure on the static system, these two together are called a pitot-static system. or a pitot-static tube, a pitot tube plus a static system. And so on this side, we've got the static pressure. Again, we could measure the difference in heights on this and actually take the difference between the total pressure and the measured ambient static pressure and get an expression for the dynamic pressure. This gives us a way to measure airspeed. So if I solve Q, the dynamic pressure here for V, then I've actually got a way to measure airspeed. And that's exactly what a pitot-static system does. It combines the pitot, it takes the difference between pitot and static pressure. Now, the challenge here is that I often don't know what my density is. There's no such thing as a densiometer. I can calculate the density of air, but I can't just measure the density of air and thus calculate true airspeed. Therefore, we usually have to work to true airspeed through a couple different mechanisms. Now, I could use other densities here. Let's say that I used, I don't know what the real density is. I know what the density at sea level is, standard sea level. Let me just use that. So if I put sea level density in here, I'm going to get a different kind of airspeed. This value goes up, which means that this is going to go down. That is going to give me equivalent airspeed. So if I use sea level density, I'm going to get equivalent airspeed. And in the iced-T equation, so something that I definitely recommend that you put somewhere in your book or on your sheet is this the radical, the iced-T radical. Equivalent airspeed is the lowest airspeed in that radical because it's the one with the highest density. Again, here's the steps. We'll walk through it very quickly. Definitely make sure that you can explain to your roommate, how do I go from indicated airspeed to ground speed? So indicated airspeed is what the airspeed indicator on the cockpit shows me. There is always going to be a position error. The fact that my static port on the aircraft is in the flow field of the air going around the airplane. That fact is going to change the fact that the air has to move. It goes around my airplane. Its velocity is going to change, so its static pressure is going to change. So I'm not going to be able to perfectly measure the free stream static pressure. That error we actually measure in flight test, and we tabulate it. It's called position error. So if I add that position error to my indicated airspeed, then I get calibrated airspeed. Calibrated airspeed, I can correct for this thing called the compressibility factor. One of the pages I recommend that you tab in your book, the table of compressibility factors. And then if you multiply the compressibility factor by the calibrated airspeed, you are going to get equivalent airspeed, the lowest of them. Again, good sanity check. Calibrated can either be greater or less than indicated airspeed depending on the sign of my position error. Is it negative or positive? But equivalent airspeed is always going to be less. That's why we draw the radical, the iced-T here. True airspeed is always going to be greater than my equivalent airspeed, and it's also going to be greater than my calibrated airspeed. And so the inverse square root of my density ratio multiplied by the equivalent airspeed is going to be given my true airspeed. And then I need to account for the what is the wind doing. So the fact that my true airspeed is my airspeed relative to the air mass, that air mass may be moving across the ground. So just think about it. If you have a tailwind, you're going to be moving faster across the ground as you're moving through the air mass. So add a tailwind to get ground speed. Of course, if you have a headwind, you got the wind in the lips. You're not going to make movement across the ground as quickly, so a headwind is going to decrease your true airspeed, and your ground speed is going to be less than your true speed. So that's the iced-T equation. Here are all the definitions for you to review. All right, viscosity. A little quiz that you can give yourself here. Remember, viscosity is defined as actually what produces the shear stress. So we have this velocity gradient, this dV dy in the boundary layer. We'll talk about boundary layers in just a second. And this velocity is a parameter that converts my velocity gradient into a shear force, into a shear stress. So again, this has units of pressure. It's a shear force. And so my viscosity is going to have units of slugs per foot per second or kilograms meters per second. And it's also tabulated in the table, in the atmosphere tables. If you notice in the atmosphere tables, as you go up in altitude, your temperature decreases until it doesn't, i.e. the stratopause, stratosphere, stratosphere. And your viscosity is decreasing as you go up in altitude because the temperature is decreasing. One of the very important distinctions, and it goes back to that point that the liquid fluid molecules are closer to each other, intermolecular forces dominate. Therefore, as temperature decreases and there's less vibrational energy of the liquid molecules moving around, those intermolecular forces are going to have stronger effects. So viscosity for a liquid increases as temperature decreases, which you know the honey gets stickier, the syrup gets stickier as the temperature decreases. A gas is exactly the opposite. In a gas, viscosity is caused by the diffusion of momentum. The fact that you have fluid elements moving through a boundary layer, and there's nothing that keeps them from carrying their higher momentum high in the boundary layer, lower into the boundary layer. And we'll talk about that in a minute. So as temperature increases, i.e. the average kinetic energy of the molecules increases, the molecules are bouncing all around, that diffusion is going to happen more quickly. So viscosity increases for a gas as temperature increases. Exactly opposite that from a liquid. All right, we introduced this concept of the Reynolds number, which we use to predict the transition point from laminar flow to turbulent flow. So remember, laminar, all the fluid elements are not, they're very well behaved. And then there comes a point where there's, it starts to oscillate in the boundary layer, and then it breaks down into chaos on this route to turbulence. And so we can predict that point using the notion of the critical Reynolds number. When the local Reynolds number is calculated by this X distance down a plate reaches 500,000 or 500,000, that's the critical Reynolds number. That's the point where the flow has transitioned from laminar flow to turbulent flow. And here's an example problem that you can work. You can see where on the B2, as a percentage of the chord, do I reach the critical Reynolds number. And in this case, it's 1% of the chord, just over 1% of the chord. So 99% of the flow over the B2 is going to be a turbulent boundary layer. Other points to keep in mind with between laminar and turbulent flow. That turbulent flow, because there's more diffusion, more mixing of these streamlines don't cross. Remember, this is in 3D, so they're all wrapped around each other and curling around each other and getting deeper and deeper in the boundary layer, taking that higher velocity flow, up here at the edge of the boundary layer, which we define as 99% of the stream, that turbulence gets deeper into the boundary layer. So your velocity vector right here next to the surface is going to be greater than it is here in the laminar boundary layer. That means that if you zoom into the molecular level to the surface level, where even a perfectly smooth surface is going to have, these big Olympus Mons, these big Himalaya mountain ranges of surfaces, and an air molecule fluid element can't go through that. It's going to exchange momentum. That exchange momentum at that surface layer is what causes friction. And so if you have a greater velocity vector down here than you do here, you're going to have more MV from that fluid element, creating more friction. So there's going to be more skin friction with a turbulent boundary layer than with a laminar boundary layer. This slope right here, well, we'll come back to the dV dy. A very important point, and we'll make it a couple more times, turbulence and separation are not the same thing. Turbulence helps prevent separation. For when we talk about adverse pressure gradient, we'll get to that. And then transition and separation are not the same thing. So the transition here occurs where the local Reynolds number is 500,000, where the local critical Reynolds number is 500,000, and the transition point, not the same thing as separation. All right, so here's a good picture of the boundary layer. So here we've got the nice layered laminar. Here's this transition region. You can start to see it starts on this pathway to chaos. And then we have fully turbulent flow here. And you can see, look at the thickness of this turbulent boundary layer here compared to the thinness of the laminar boundary layer. Now, this is going to result in greater skin friction because we have that deeper velocity gradient, so more skin friction. But when we talk about separation and pressure drag, turbulent boundary layers are going to delay separation and will reduce pressure drag. And we see that right here. So the two-dimensional drag, when we talk about 3D airfoils, we'll add one more. But the profile drag, so when we take a 2D cross-section, 2D profile, there are two components. There's the pressure drag, which is the difference in the pressure between the front and the back of either the blunt object or the streamlined object. There's a pressure difference between the front and the back. That's pressure drag. And then the friction drag, the fact that there is the velocity gradient, the velocity at the surface has to be zero. And it is zero because that MV runs into little surface imperfections and transfers the momentum and goes to zero velocity, and that exchange of momentum is friction. So if we look at a streamlined object like this, that's dominated by skin friction drag, you can see at low Reynolds numbers, we actually have lower skin friction coefficients below than we do for turbulent boundary layers. But then we have this transition region, and we actually have the turbulence and skin friction increases, but when we normalize it, we can actually get lower drag due to a decreased separation, lower skin friction coefficient, which again is normalized by the overall size. So the drag's not lower, but the skin friction coefficient is. The best way to look at this is let's compare this streamlined object with this blunt object. So we have a little cylinder here. That's 1/10 of the width, the dimension of the streamlined object here, and they both have the same drag. However, this one is dominated by the pressure difference. The fact that the airflow separates and you have this low pressure wake behind this cylinder, and you have the stagnation point on the front side. And so there's a large pressure difference, high pressure on the front, low pressure on the back. That results in a big pressure difference. That's pressure drag. That's what the blue is right here. And it's dominated by that pressure drag. However, here we have dominated by skin friction drag, but the same total drag. So you can have something much larger, 10 times as large, with the same amount of drag by streamlining. And that has very important implications when you look at like biplane, wire struts, wires to support the struts, and all the drag that came from that. That also explains why a blunt object, why we want dimples in our golf ball. This encourages turbulence, which makes the airflow in the boundary layer more resistant to separation. We'll show you why in just a second, but we don't want to put those dimples in our sailplane wing where we're dominated by skin friction drag. So skin friction dominates here, pressure drag dominates here. So we want a turbulent boundary layer. We want a laminar boundary layer. So let's talk adverse pressure gradient, which is what drives the separation point. There's this point in the wake where the airflow is no longer attached. We say that the airflow is separated at this point. This is the separation point. Not the same thing as transition. Transition occurred right here. So here was laminar boundary layer. We got to the point where their local Reynolds number was 500,000, and then we transitioned to turbulent airflow, turbulent boundary layer. At some point, we separated. Now recall, and we saw this in the airfoil lab, you can actually have separation before you've had transition. So the Reynolds number in the airfoil lab was less than 500,000. The chord-based Reynolds number was about 450,000. So that entire airfoil was laminar, but we still got separation on the leading edge. Remember the tufts that we had, the little threads, the wacky wavy inflatable tube dudes on the airfoil. So this brings up the concept of adverse pressure gradient and what actually causes the separation. So on the airfoil, that low pressure area is the lowest pressure was right here on the front, and the high pressure area, we get closer to the what we call the recovery pressure on the backside here. Air normally likes to go from a high pressure to a low pressure, and here we're forcing it to go, as the streamlines go this way, to go from low to high. So that is known as an adverse pressure gradient. We are forcing the air to go essentially upwind. And so some of the air, and it sneaks along the boundary layer here, where the airflow is not that much, these little fluid elements sneak upstream. And that's what this adverse pressure gradient does, what this airflow does in the boundary layer. So here's a really good example. So here's our low pressure up here, high pressure back here on the airfoil. And so the fluid elements are trying to go from high to low, and they're able to do that right up the boundary layer where the velocity was very low. And so if we have a turbulent boundary layer where these velocity profiles are greater, deeper, then they have more ability to overcome the fluid elements that are trying to come upstream. At some point, the fluid elements coming upstream, you can see here they've already moved upstream, are going to completely counter the velocity of the airflow coming downstream. When that occurs, a fluid element here is just going to take the path of least resistance. This is where we say the airflow has separated. In that point, we saw in the airfoil lab, starts very at the trailing edge of the airfoil, and as the angle of attack increases, moves forward on the airfoil, that separation point, until it reaches the leading edge. And this is a post-stall. So right here at in this case, at alpha equals 16 stall, the separation point is indicated right here. In the airfoil lab, we saw it about right here with the threads and what they were doing. So if we have a turbulent boundary layer, that velocity profile is deeper and it's more able to force past and force, those fluid elements coming upstream. A greater velocity coming downstream is easier to say, hey, no, we're going to go this way. We're going to go downstream. And the fluid elements are able to do that. So that's why turbulent boundary layers are more resistant to separation. Separation, again, is where the airflow is no longer attached to the surface of the airfoil. We don't like complicated, the concepts themselves are complicated enough. We didn't need to complicate them with the terminology. So separation is the point where the airflow separates. Transition is the point where the flow transitions from laminar to turbulent. Transition and separation are not the same thing. All right, so the adverse pressure gradient is defined as if the x direction, if x moves aft, so if x is 0, x increases this way, and then low pressure, higher pressure, again, this is a negative scale right here on top, and so low pressure to high pressure, this is a dp dx greater than 0. That is known as an adverse pressure gradient. And as the angle of attack increases, so here is 0 degrees angle of attack, there's 4 degrees angle of attack, there is 8 degrees angle of attack. So that value of dp dx as the angle of attack increases is getting higher. It's getting more adverse until the point where the airflow can no longer accommodate it, and that's what causes separation. All right, so here's a table for you to review on your own with the differences between laminar and turbulent and Reynolds number. Again, if you can explain these different concepts and these differences to your roommate, and it'll benefit them, they've got to take Aero 315 at some time, then you're going to be in good shape for the GR. All right, so let us talk. Actually, there's one concept we missed, which was the idea of center pressure. Actually, that's still coming up. All right, so we are going to use the NACA, the National Advisory Committee for Aeronautics, 4-digit series. And that's what you've got the charts in your book. So in the NACA 4-digit series, the first digit, recall, is the camber, percent camber in percent of the chord. So in this case, 4516 is 4% cambered. The second digit is the location of the maximum camber, i.e. the maximum deviation between the chord line and the mean camber line, which is the kind of the middle between the top of the airfoil and the bottom of the airfoil. So that maximum distance, where does that occur, is the second digit. And then the maximum thickness as a percent of the chord are the last 2 digits. So 4516, 16% thick, halfway, 5/10 is where the maximum camber is, and it's 4% cambered. This is just for your awareness, not something we're going to question on the GR, but those are the equations from the NACA report. So this is what NACA has charted for you for the entire family of airfoils. So 2415 here, there's a depiction of the airfoil. You got section lift coefficient here, drag coefficient, moment about the quarter chord, and moment about the aerodynamic center, and we'll review those very quickly as well. You're going to need a straight edge on the GR. I would also, as you're looking up different questions, don't hesitate to use a pencil to draw across to make sure that you're reading, because it's easy to misread the charts if you're just using your finger. So use a straight edge. Reynolds numbers over here. Remember this 3 million, 6 million, 9 million. This 10 to the 6 goes with all these. We are not going to use the standard roughness. These symbols are not easy to distinguish what they are, but again, based on the theory of what Reynolds number are, and we'll go over it very quickly, remind you, tell you that the highest Reynolds number should be up here, and the highest Reynolds number should be on the bottom over here as you increase section lift coefficient. You've also got the location of the aerodynamic center. So let's take a look. This is out of the NACA report. This is the lift curve slope, CL alpha. And if you look, they're all about 0.1. And when for the aero majors, when you take Aero 442 and you do thin airfoil theory, you'll actually derive the fact that the lift curve slope for a thin airfoil is 2 pi per radian, or 0.1 per degree. So you'll just use that. You don't have to look it up in the chart and take the time to actually measure the lift curve slope. It's 0.1 per degree. Another nice rule of thumb here. So here are symmetric airfoils, double O's. Look at the alpha lift equals 0. It's all very close to 0. It's all 0, which you would expect. A symmetric airfoil at 0 wave attack should produce no lift. Here are the 2% cambered airfoils, the 2000 series. And if you look, 0 alpha angle of attack is all about -2 degrees. Look at the 4% cambered, it's all about -4 degrees. So the rule of thumb is that the alpha lift equals 0 is the negative of the camber. So 2% cambered is -2 degrees, alpha lift equals 0. 4% cambered is -4 degrees, alpha lift equals 0. So that will also save you a little bit of time. Another set of equations that you should memorize. Again, reminder, the nomenclature, we're using lowercase for 2D. We're going to talk about 3D in just a second. So lowercase values. But again, if you have to look up the definition of CL, CD, lift and drag coefficients and the moment coefficient, you're just going to run out of time. All right, so very briefly, center of pressure. I always like to equate, in my mind, center of pressure is equivalent to center of gravity is to mass. So, of course, gravity acts on every molecule throughout an object, but that's kind of inconvenient. So we treat this point called the center of gravity, and we say, hey, weight acts through that point. Force, pressure over an area, so that pressure acts all over the surface of the airfoil. There is a point where we can say that pressure acts through, and that's the center of pressure. So the center of pressure is that point where the center of pressure acts all the way through. Just as we can move the center of gravity in an object anywhere in the object, if we move it from, kind of the centroid, the center of mass, we're going to have to introduce a moment to account for the fact that we're not putting the center of gravity at the center of gravity, at the centroid, or at the center of mass, or at the center of where the mass is. Same way, if we were to move the center of pressure, and the reason we might want to do so is because of the fact that as angle of attack changes, the center of pressure changes, which becomes very inconvenient when we have to do the stability, sum all the moments in order to stabilize the aircraft. We don't want to deal with the fact that this lift force is moving around on the airfoil. So we're going to find a point where we can move the center of pressure. If we move the center of pressure forward, we are going to have to introduce a moment, a nose down moment, to account for the fact that we've moved it forward. And so if we take a look at that, so if we move the center of pressure all the way to the leading edge, we're going to have, as the angle of attack increases, an ever increasing negative moment. That's not what we wanted. If we moved it all the way back to the trailing edge, we actually have to add a nose up moment to account for the fact. So the fact that that's way up here and that's there means that there's somewhere in the middle where that moment that we have to introduce is constant. That's what the aerodynamic center is. So the aerodynamic center is the point where if we put the center of pressure there, and of course we have to add a moment when we move the center of pressure. Well, center of pressure is the point where there is no moment. If we put the forces of lift, or the resultant forces, the pressure drag as well, through the aerodynamic center, the moment is constant. So center pressure, there is zero moment. The aerodynamic center, the moment is constant as angle of attack changes. And that's exactly what the aerodynamic center is. For subsonic airfoils, it is very close to the quarter chord. You can see off for this 2412 how it is moving closer to the quarter chord as angle of attack increases. For Aero 210, we will say that you will treat it as the quarter chord. And if you look at the NACA chart, you'll see it's 24%, which is really close to 0.25. For subsonic flight, once we go supersonic, and we'll talk about this in a couple lessons, the aerodynamic center moves to the half chord. And in Aero 241, you'll derive why. Of course, for a symmetric airfoil, there is zero moment about the aerodynamic center. All right, we already covered this briefly, but again, Reynolds number effects. So as the Reynolds number increases, more of the airfoil is going to be in turbulent airflow. So higher Reynolds number could be caused by higher velocity. That transition point from laminar to turbulent is going to move towards the leading edge of the airfoil, which means more of the airfoil is now going to be turbulent. Turbulent boundary layers are more, can overcome that, are better able to overcome that adverse pressure gradient, are therefore more resistant to separation, and will therefore reach a higher angle of attack and a greater CL max before they stall. Same way, as the angle of attack increases, that streamlined airfoil starts to act more like a blunt object, in which case it is going to be more dominated by the pressure drag. And so the decreased separation or later separation is going to result in a decreased pressure drag. So you're going to have a lower drag compared to a lower Reynolds number. For a higher Reynolds number is going to have a lower drag at high angle of attack than for a low Reynolds number. All right, so that was 2D, but unfortunately, or fortunately, I guess for us, since we are 3D animals, we live in a 3D world. So there's high pressure underneath the wing, low pressure on top. Of course, that difference in pressure, difference in force, is low pressure on top is still pushing down, but the high pressure on the bottom is pushing up more. The net result is that there's this net force up that we called lift. Well, that high pressure air nothing is going to keep it from sneaking around and going from that high to low. And so you can see the effect of that, that wingtip vortice in this photograph of an airline coming into land. This is going to introduce another type of drag, and it's also going to change our lift. So this downwash changes the airflow in the vicinity of the wing here. So this downwash in the vicinity of the wing causes a net, what the wing actually sees. Here's our free stream velocity, but there's a net downwash caused by the fact that this vortice is coming around, and so the real wind that the wing sees is going to be this angle right here, which is decreased. So here's the free stream, there's the relative with the downwash. So we've actually decreased our angle of attack by this induced angle of attack right here. So our effective angle of attack is this, and here's our induced. You can actually derive how much of that occurs, and as lift increases, that angle, that induced angle, that downwash angle is going to increase. And this is a closed form solution for elliptic lift distribution. Very convenient, so we actually use it for all wings, even if they're not elliptic, but we correct it by introducing this span efficiency factor, some number less than 1. So the way I remember this is CL over pi in your ear, and this is radians. So if we want it in degrees, then we need to do the radian to degree conversion. So 57.3 CL, and this will give us a downwash angle in degrees. So the net effect then, when we look at a 3D wing, is, here's our 2D wing. CL alpha is the lift curve slope. That's the definition of CL alpha. And again, we already showed in the charts that it's 0.1 per degree. By theory, it's 2 pi per radian. Use 0.1 per degree. And if you account for the downwash angle and how is this slope going to change, then here is your lift curve slope for a 3D wing. Now notice it was caused by lift. If lift is 0, if CL is 0, then there's no induced downwash. There's no there's no reduction in effective angle of attack because there is no downwash, because there is no lift. And therefore, the alpha lift equals 0 is the same for the 2D airfoil, for the infinite wing, or the 3D wing. So the same effect there. Once we have the 3D lift curve slope, this is just the equation of a line. So here's slope times essentially the effective angle of attack, if you will. So angle of attack minus, remember this is often negative, so you have negative minus a negative, so you're actually going to add. So in this, let's say that this was 0.08 per degree, and I had at 6 degrees, what did I, if I want to know what is the lift coefficient at 6 degrees, and it's a 2415 airfoil, so it has a -2, alpha lift equals 0, so 6 minus -2 is actually 8 degrees. 8 times 0.08 is 0.64. So my lift coefficient is going to be 0.64. Once I have my lift coefficient, I can now actually also calculate the 3D drag. So lowercase, two-dimensional profile drag, that comes from the NACA chart. Profile drag is a combination of the skin friction drag and the pressure drag. And to that, I add this term, this induced drag, this drag due to lift. As it goes up with the square of the lift, and so we have CL squared over pi in your ear. And so our total 3D drag is a function of 3 different kinds of drag. There's the skin friction, which again for a streamlined object is the dominant form, but as angle of attack, pressure drag increases because there's more separation points, so there's more of that low pressure region behind the airfoil, sucking it back, if you will. And then I've also, in a 3D world, I've got the fact that I'm dragging this vortex behind me. Another way to think about it is I've tipped that lift vector back relative to the relative wind, but I really cared about it relative to the free stream wind. That's what the source of that induced drag was. And now you have an ability to calculate it. And so here's your algorithm. I would make sure you write this in your book somewhere. Those are all the equations. This is how you approach going to a 3D finite wing. We'll modify it slightly when we get to airplanes, but if your airplane is a wing, then you're all set. So what's an example of where your airplane is a wing? We'll get to that in just a second. Page 173 in your text, definitely one of those pages I would tab. We've only done this section in the first 13 lessons, 2D airfoils and 3D wings. We're going to slightly modify the 3D wings in order to account for the entire airplane. That is coming after the GR. Don't forget some of your airfoil nomenclature. One of the ones that you'll use over and over again is the aspect angle. Angle equals b squared over s. Aspect angle, aspect ratio right here. You actually need it as the very first step to find the CL alpha, the three-dimensional lift curve slope. So aspect ratio b squared over s. So if your aircraft is a flying wing, i.e. a B2, you can solve for this. So I would encourage you to pause the video here, take out this worksheet, and make sure that you're going to work this problem. So we have a 250,000 pound B2. Did I say B52? That's clearly a B2. Flying at 0.3 Mach, so it's flying in the incompressible region. And I want you to calculate the lift and the drag. So go ahead and pause the video and come back once you have an answer, and you can check your answer. And here is the answer. Welcome back. So again, stepping through the algorithm. And when we get to the bottom here, so we have a total of, we calculate the angle of attack. We need 5 degrees of angle of attack for this 2415, and the 2415 is just an approximation. Good enough for our first order engineering practice here. So we need about 5 degrees of angle of attack to fly at 0.3 Mach. That corresponds, when you go through the math, of about 11,000 pounds of drag. So what's our lift to drag ratio? This is a good sanity check. And again, I already pointed out the point at the start on the GR. If you get a wrong answer but exercise good engineering judgment, you will receive, you'll lose points for the wrong answer, but you'll get points back for good judgment. In some cases, I've had cadets get back as many points as they've lost because they've exercised good judgment and they've pointed to where I think I went wrong here. I just don't have time to fix it. So if we look at the lift to drag ratio here, 22.6, which is exactly what we'd expect for a kind of a bomber transport airline type of aircraft, about 20 lift to drag ratio. Fighters are in the neighborhood of 8 to 10 is a typical value. When you get out of the airfield and fly the gliders and the glider IPs, your lift to drag ratio down there is going to be 40 to 50 lift to drag ratio. So again, you're starting to build an appreciation, intuition for what are these engineering parameters and what should I expect. All right, so that is a lot of ground. High-speed pass. Again, if you have questions, we're available for EI throughout the week. As my wife said to me every morning when I went off for a check ride of pilot training, and it's good advice for you as you approach the GR. Good luck. Don't suck.